Welcome in, everyone. Thank you for being here. Grab yourself a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have some calculus on the board. These problems do not come from me. I won't take credit for them. They come from, I believe it's Samuel Schachter. I'm not sure if they're his original materials, but that's just where I got them from. And here we have some routine exercises in antiderivatives and differential equations. So I want to show you sort of the difference between antiderivative, indefinite integral, definite integral, just to clear some things up here. So you're welcome to attempt these problems. If you're going to attempt them, they're done by hand. I really think they should only take about 6 or 7 minutes total, maybe even only 5 if you know what you're doing right away. Notice that this one does not need you to solve. It just wants you to change it to U form. That's all you have to do. So once you can change it using a U-Substitution, you're good to go. And we're going to talk a little bit about that. So feel free to answer these, pause the video, give yourself some time to try these problems. And now I'm about to start explaining them. Let's begin with number 1. Number 1, this is called a differential equation, as indicated by the fact that it says solve the differential equation. This differential equation is essentially just a derivative equation. So you might just want to think of this as a derivative equation. It tells us something about the derivative, and you'll notice that in this case, the derivative only depends on x. So this is not an implicit differentiation kind of scenario. It just depends on x, which means we can find what y is. We can also use this along with the fundamental theorem of calculus, but let's be clear on what it means to solve the differential equation. What it means is find like y equals f of x. Find the exact equation that has this point on the equation and whose derivative is sin over cos cubed. All right, so we're going to combine these several ideas that I just mentioned together. We're going to start off by setting up the fundamental theorem of calculus. So let's take dy dx and multiply dx on both sides. That's going to get us sine of x over cosine cubed, and then dx. Now, since these two differentials are equal, we can add them up indefinitely, and they will still be equal. And when we do the integral of dy, or the antiderivative of dy, that's just going to be y. But when we do the antiderivative, or the integral of sine of x over cosine cubed x, that can be a little tricky. There is more than one way to do this. I'm sort of curious, for those of you who tried, maybe you can mention which method or which approach stood out to you. This can be done sort of directly by a U-sub at this point. And remember that we're going to have plus c when we do this, because this is an indefinite integral. It does not have limits. So what we're looking for right now is kind of like a function or an antiderivative, not a specific value. That would be a definite integral, which finds the specific amount of area underneath a curve from a starting point to a stopping point. Okay, so if we do this with the U-sub, let's make U equal cosine of x. That's the thing on the bottom. A lot of times when you're doing a U-sub to solve an integral, especially in Calc 1, you're going to be substituting the denominator or something in the denominator or something in a radical. That's often the case. And if we allow u to be cosine of x, we see that du is pretty much there. in a slightly different format. Negative sine x dx, that's almost there. So we can sort of counterbalance this by putting a negative and putting a negative. So it counterbalances the value of the integral because a negative doesn't change the value, but we've sort of included a negative that way we can smoothly replace negative sine x dx with du. So now we have 1 over u cubed du, which we can also call u to the minus 3 power. That could be useful since we're going to be taking an antiderivative. How do you do that with the power rule? You raise the power by 1, and then you divide by the new power, and we can't forget plus c since this is not definite. 1 over 2, u to the negative 2, so I can put cosine squared back in the bottom. And so I could just call this 1/2 secant squared plus c. Okay, that is a valid equation for y. It just isn't a specific equation for y because of that. You might wonder, secant squared, wow. If you take the derivative of secant squared, does it really turn back into this? I guess it's positive secant squared too. It's like, does it really turn back into all this? Interesting. Yeah, it does. Now, if we use the initial condition, which said that y of 0 equals 3, we're going to use the point 0, 3, and this will be 3 equals 1/2 of secant of 0 squared. Secant's 1 over cosine, everybody. Shouldn't come as a shock. 1 over cosine squared is secant squared, just like we have here. So cosine of 0 is 1, 1 over 1 is 1, 1 squared is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and plus c. So 3 equals 1/2 plus c, and that way c equals 2.5 or 5/2. Doesn't really matter. Either way, we need to plug that into the equation. Now we can update our equation and say y equals 1/2 secant squared x plus 5 on 2. Okay, that is our equation. Pretty straightforward. There's a little bit of a u-sub here, but as I mentioned, there is another way to do this problem. Let's investigate what that other way is. Well, sine over cosine cubed can also be written, ready for this? It can also be written as sine x over cosine x times 1 over cosine squared x, which is tangent x, times secant squared x. So if I want to integrate that, I can do a u-sub because this, well, let me include the dx. There's a dx that's supposed to be chilling. This would be my du if tangent is my u. So let's see exactly how that works. That's going to be the integral of u du, which is simply 1/2 u squared plus c. But if I put the u back, this is 1/2 tan squared plus c. But wait a minute. I thought y equals 1/2 secant squared plus c. How the heck are we getting 1/2 tan squared plus c? Secant squared and tan squared are completely different functions, right? 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 Those can't be the same. Tangent squared and secant squared, those must be different. Right? Do you get what I'm hinting at here? I'm not saying secant squared and tangent squared are the same. If you think that, you're reading a little bit too far into it. What I am suggesting is that there's a very intimate relationship between these two. Do you remember this Pythagorean identity? secant squared equals tan squared plus 1. So this constant is going to be a different constant than this one, but it's going to be a constant such that these two functions are equivalent because secant squared and tan squared are basically the same. They're just off by 1. So let's use the initial condition again on this function, which is written slightly differently with tan instead. And we say 3 equals 1/2 tan squared of 0. Tan of 0 is just 0, so tan squared is 0. And here we get c equals 3. So an equivalent function is that we have 1/2 tan squared plus 3. Now, how are those two the same? Well, let's look at secant squared. And instead of secant squared, remember the other equation that we had? Instead of secant squared, I'm going to put tan squared plus 1. And then my c was 5/2. So this is going to be 1/2 tan squared plus 1/2 plus 5/2. That is the exact same equation. So very interesting that you can get a completely different answer, or not completely different, but it looks different. It looks very similar but different answer by doing a different method of integration. And whichever one stands out to you the most, whether it's to split up this sine over cosine and this 1 over cos squared and then use a u-sub, or if it's just to sort of directly use a u-sub by looking at it and saying, hey, cosine on the bottom, and we have sine on top. So, yeah, pretty straightforward to use a u-sub that way as well. Okay, so moral of the story is that this function works, 1/2 secant squared plus 5/2, and 1/2 tan squared plus 3 also works. Yeah, great problem, really great problem. Okay, now we're going to look at a definite integral. And definite integrals with u-sub are pretty convenient if you fully transform the integral. What do we mean here? Change to u form. We basically have everything with an x must turn into a u. That's what we need. Once we've done that, we are successful in the u-sub. So let's see what we've got here. Of course, inside of the radical, pretty clear that that's going to be our u. If you can't see that, I'm sorry, it's a little bit blurry. So u is going to be x cubed plus 4. That's what's inside of the radical. So du is going to be 3x squared dx. That changes pretty much everything to x's. So this x squared is going to get turned into something with a u. This x cubed plus 4, the whole thing is just going to become u, and the dx is going to change as well. We're going to have a du. But what else is there to change? We have to change the limits. These are x limits, and we're not going to be in the x world. We're going to be in the u world. We're transporting everything into the u world. I don't know if you've ever seen or heard of Blue's Clues, but there's a popular thing that would happen where a human character would, supposedly, obviously, they would use video editing effects, would jump into a photograph where, like, I don't know, some little characters were playing, and then he would be interacting with them. It's sort of like we're going into a completely different universe. The U universe. You can call it the universe as a pun if you really want to. But what that means is that there's like a portal to this other dimension, and it takes all of our x values and turns them into u values. That portal is the u equation here, x cubed plus 4. That is the way that all the atoms are going to be rearranged when you go through that portal from the x world into the u world. So what I'm saying here is that u of 0 is going to create a new value as the limit of integration. This is going to be 0 cubed plus 4. And u of 2 is going to turn into a new value. It's going to be 2 cubed plus 4. So one last thing we have to do to change this integral. Notice that we don't have 3x squared. We do have x squared. So we're going to go from 4 to 12. Those are the new limits. We need a 3x squared to be in front. So we would have had to multiply by 3, which means we would have had to also divide by 3 on the outside. And now we can simply replace this as square root of u du. Or if you'd like to call it 1/2 power, that's fine if you're going to get ready to integrate it. You don't have to integrate this one. I mean, hey, if you do it, by all means, go for it. It's just they're not going to come out to pretty nice numbers or anything like that. So you'll just have radicals left. Yeah, square root of 12 is not necessarily like a nice number. But the idea here is to practice turning these into different limits, and then, let me tell you, all you have to do is solve this new integral as if this was the entire problem from the beginning. You don't have to put it back into x. That's the benefit of fully committing to the U universe. Okay, so that is the integral expression. It will give you the same value as this will. In fact, you plug them both into a calculator and see for yourself. Okay, let's look at number 3. Number 3 is a very common way for them to sort of throw you off. It's a very simple, sort of a cheap tactic. That's how I like to think of it. Oh, they're trying to get me with this cheap tactic. Don't let them fool you with this. It may seem like, well, we don't know the quotient rule, or do I have to do a U-sub with the thing on the bottom? What's going on there? Now, if you think about this carefully, we can simplify this expression. We can just divide, or sort of like use the rules of exponents to realize that this is x plus 5x squared over x to the 1/2 power, which means that I can reduce these terms. In a sense, what I'm technically doing is I'm factoring out x to the 1/2 on the top, and that just leaves me with x to the 1/2 plus 5x to the 3/2. What I did there is I essentially just subtracted a 1/2 power from both of those exponents, and so the 1 turned to a 1/2 and the 2 turned to a 3/2. Pretty straightforward, and that's going to cancel perfectly. So nice with this x to the 1/2 on the bottom. And we've simplified our expression. We might as well keep it in this rational power format because we're going to have to use the power rule in order to take an integral. Okay, so that's straightforward. Increase the power. So that's 3/2. Divide by the power. Just don't even think about division. Just flip it and multiply. Literally just flip it and multiply. Don't overthink this. Plus 5 times, this is going to be x to the 3/2 plus 1. That's 3/2 plus 2/2. Divide. Just don't even think about dividing. Just literally flip it and multiply. And then we can't forget good old plus c. So let's see, does anything simplify here? Yes, it does. The 5's cancel. So this is just going to be 2x to the 5/2 plus c. So I wouldn't be surprised if you get a problem like that on like a multiple choice section from the AP exam, to be quite honest. And the last one here. So again, these are made to look intimidating, but the reason why we're practicing these antiderivatives is because you need to be able to take an antiderivative in order to do any integral problems at all. And so you need to be on your toes, look alive, and see what they're trying to trick you with, right? So look alive, but don't freak out, don't panic. Just think, how can I simplify what they gave me? So look at the bottom here, cosecant times cos squared times sine. There's got to be a way something can simplify there, right? There's got to be. So let's take cosecant and sine. Cosecant is 1 over sine times sine. I mean, can you make it any better than that? They just cancel. So we have integral of 3 over cos squared. And then we should probably rewrite that because we know that 1 over cos squared is just secant squared. And that is a nice derivative of something, right? Like that's already the derivative of something that we're familiar with, which is tan. So this is just going to be 3 tan x plus c. And this problem is I'm sure you'll admit, much easier than it looked. We just had to simplify it first. All right, so these are some of the things that you should be looking out for when you're studying for the AP exam and when you're taking the AP exam, and any exam, to be honest, but particularly the AP exam. Right? There's something about the way they test you that if you're aware of how they test you and what kinds of things they're trying to do to trick you, it makes you much more competent for passing that test specifically. I won't say that it makes you better at understanding calculus. That's what I'm trying to blend here. So I'm trying to blend the concepts of calculus and the test-taking strategies of approaching the AP exam for you students who are studying for the AP exam. If someone were in a college calculus class, this is probably super boring. This wouldn't benefit them at all. It's just like pure study hall. But if you're studying for the AP exam, this is going to be particularly useful for identifying some of the kinds of tricks or curveballs that they throw at you, right? I'm really prepping you for this fight. All right, I think that's enough blab out of me. If you need to go back and watch anything again, feel free. In another video, we'll take a look at tan squared plus 1 and secant squared, and we'll look at them on a graph, or I encourage you to look at them on a graph, and you'll see their similarities. Very similar. All right, that should do it for me. I'll see you guys next time in the void.